Hello everyone, I am Mohammed Saad, one of your fellow students at IBM Advanced Data Science Specialization and its Capstone project. By background, I am an engineer from NED and by profession, I am a business manager. Moving toward data science. Today, my project is human activity recognition. The dataset for this project is taken from UC Irvine machine learning repo. I've pasted a link here. You can see it is an amazing repo. They have many data sets from medical to engineering and interesting topic like wine or medical imagery and etc. You can see it yourself. The data set I have taken was taken in a closed environment of 15 participants with around 1.92 million samples. You can see I have taken the image from my code here. We have around 1.92 million instances with 7 labels, and the data is starting with minimum values. You can see we have already defined some of the outliers here. The mean between the mean and the variance of the data was few lessons that later. Well, use cases. This data that I've taken can be used for mobile apps for like activity detection and guiding human for if they are performing something, so what to perform next, or predicting what they will be performing next, or performing exercises. The apps that will support exercising and seeing how will human performing on a certain exercise if they are taking the wrong movement or not. Similarly, since we are in a COVID era, the demand for VR and AR is exploding. So this type of data can be used for recognizing human posture in scenes of games. Like if you're walking in a game, how it will convert in a VR or AR environment. This will help in this kind of project as well. Well, for solution, I have a Jupyter notebook which is deployed on GitHub. Here's the link for my project as well. I have divided the book in two. The first book was for initial data exploration, data visualization, as well as checking outliers and performing a little bit of fun to see how correlations work. And in the second notebook, I have selected my models. We'll discuss about it later, by which and what model I have chosen, as well as hyperparameter tuning and the output, why certain models were selected, and how much accuracy it had gained, and the confusion metrics in the end as well. So our presentation, okay, we have selected model for both supervised and unsupervised learning. Architectural choices, well, Jupyter Notebook was always my first choice because I'm kind of in love with it because its performance is exceptionally well, and it's now uh, it's good that it can only also be uploaded in GitHub. Also, GitHub is a good place to showcase what improvement you are getting in your skills, and to show the world how steadily you are moving forward. Also, UCI data repository. The main reason was choosing for this data set is that the data was not incomplete. Like many data you have take, it contain missing values or wrong values, or the data is so massive that you have to clean. You have to invest most of the time to cleaning it up. But kind of data which is taken in a closed environment, the chances of error are very less. And also, the Jupyter notebook I had run was an IBM Watson. It was not possible without IBM Watson because the amount of data I had was different cloud, and even my machine was taking additional times in hyperparameter tuning. Well, for data quality assessment, you can see here in a pair plot that some of our data points in X, Y, and Z acceleration. Well, you can see here that most of our data in X, Y, and Z axis is spread. Well, these few readings, which we consider outlier, are very much off the grid, and we can consider them the noise in our data, which will create problem for our models, both for supervised learning as well as deep learning. Also, we have seen a zero label in our data, although the real readings are very less, but it's still we don't have any definition of what label zero is. And by the count, you can also see that this is misleading. There is nothing like this in the data we have. Also, the biggest problem most of the R data sets, the project I've seen is of data imbalance. As you can see here, that some of our labels have very few data points and others have around more than half a million, while some have not more than 150K, not around 100K data points. This will create imbalance among the labels and might create bias for our models, in a sense that some of our data points are a model is well trained on some of the data of some of the labels, while on the other hand, it doesn't have sufficient data to train, and it might perform poor on it when it is performed on unseen data. Moreover, we have done some data pre-processing. You can see here for certain labels, I have used box plot visualization. You can see the amount of outliers. The data is very much spread and skewed, and we have to convert it in either Gaussian form or normal distribution to get the optimum results. You can see the complete box plot diagram in my notebook. Also, we can see 3D surface plots that how our data is represented for different labels in X, Y, Z dimensions, and how we can either create more features out of these dimensions, or if we can reduce it using feature engineering, which we see later. I've done some creativity to see how particular axes are performing against each other. You can see that for working at computer, the y-axis is particularly on a certain patch, while x-axis was spread around a long distribution. Similarly, for walking, the pattern is different, so I think our model will easily adopt and train on these things. It was just to see that is there any difference, or all the labels have this similarity in X, Y, or Z axis. Also, what I have done is taken a label encoder on all the labels and see if there any correlation, but there is not very strong correlations among these values, except for working at computer or talking while standing. So also in walking and talking while standing. So I think our labels we will see some false positive and negatives during training or either in unseen data points. So what we have done for feature engineering was first we dropped label zero, which was the noise for our data, and secondly, yes, this was the main part. We have converted our model, our data points into max scalar as well as power transformers. The details about both is in my Jupyter notebook. Just for information, the min-max scalar is convert data points in a particular range you give, either 0 to 1 or 1 to minus 1, while power transformer can take negative values as well and perform better spreading in a given space to reduce the size of spreading of your data. So accuracy of the matrix that I choose for model performance indicator, as well as precision, recall F1 score. Also, we have used visualization to see how our model is performing what is the loss of the training and validation data and accuracy of training and validation data as well. For model algorithm, I've chosen XGBoost classifier. We all know XGBoost is surpassing all other machine learning algorithms for classification and most in hypertune parameters regression as well. Because we have the problem of multi-label classification, so XGBoost was my first choice in supervised learning. It was hyper-tuned for certain parameters. You can see that in my notebook. And from deep learning, I've used Keras sequential model because it was uh, to check my basic understanding as well as perform and to see how good it performed with certain layers with different activation functions and number of inputs and outputs. Well, for XGBoost, I've achieved around 84.2 accuracy, while my deep learning model only achieved 83% accuracy. The main reason I will discuss in the conclusion why this happened, why the result of my model on unseen data was not up to the par. You can see here I've used the confusion matrix to see while for certain, as I've told you earlier, that we might incur bias in our training model, and that was I was fair. I was having fair, and it has happened. For the labels which have the highest number of data available, it performed extremely well. But for labels which have very few data points, the performance was poor. It also the another reason was that the spread of data, as you've seen in my pair plots as well as box plots, that x, y, and z axis for activities like standing or standing and walking or walking upstairs or walking and talking with someone have almost very close XYZ dimensions. So it was really hard for model just to work with three features, and actually having an 84 and 83% accuracy with a model where certain values correlate very much and coincides in XYZ dimension is pretty good. So my conclusion is that this model can be improved. Yes, it can go to 94, 95, or even 97 or 99% accuracy if the new features like time period or frequency for each activity can be added, or we can add two or three more sensor points, which will give us more leverage. Like if we have more sensor point around the back or around sensor nervous system, it will improve our functionality. Here we can see how X, Y, Z axis are changing for a certain period of time. While for deep learning, we can also improve our model with by adding multiple layers or fine-tune XGB or even light GBM model. Thank you.